This is a photograph of the top of a nuclear reactor. Look at the hole. That cavity is about the size of a pineapple. It goes clean through 6.5 inches of carbon steel. Under it, there was nothing left but a stainless steel liner about 1/3 of an inch thick. Behind that liner sat about 2,000 pounds per square inch of superheated water. Nobody died at Davis-Besse. Nobody was hurt. Nothing was released. That is exactly why you need to see this. I'm Ray Callahan. This was not corrosion nobody noticed. This was corrosion somebody scheduled around. Every forensic case I take apart usually ends with a body count. This one ends with a measurement. 6.5 inches of steel gone, 1/3 of an inch left, and a bulge in that last layer with cracking in it. That is the margin. That is the whole story. The Nuclear Regulatory Commission would go on to treat this as the most serious safety problem at an American commercial reactor since 3 Mile Island in 1979, and not one person got a scratch. So here is what I am going to prove to you in the next 20 minutes. First, that the plant told on itself for 6 straight years, in writing, in maintenance logs, in clogged filters, in a cleaning schedule that went from almost never to 28 times. Second, that in the fall of 2001, the regulator wrote an order to shut this reactor down and then did not send it. Third, that the difference between a boring inspection and the worst day in the history of American nuclear power came down to a document with a date on it and a compromise on that date. Not a storm, not a freak defect, a calendar. Start with what you are actually looking at, because the geometry is the whole case. A pressurized water reactor is a steel pot. The lid of that pot is called the reactor pressure vessel head. At Davis-Besse, near Oak Harbor, Ohio, that lid is carbon steel 6.63 inches thick. Call it 6.5 inches of solid steel, domed, weighing dozens of tons. Carbon steel is strong, but the water inside is borated, and borated water eats carbon steel. So the entire inside face of that lid is lined with a thin layer of stainless steel cladding. The carbon steel is the muscle. The stainless is the raincoat. Now punch holes in the lid. You have to. The control rods that regulate the reactor come down through the top, and each one needs a tube to pass through. Those tubes are called control rod drive mechanism nozzles, vessel head penetrations. Davis-Besse's lid had 69 of them. Each one is welded into the head. Those nozzles were made from a nickel alloy called alloy 600. In the 1960s, alloy 600 was the obvious choice. By the 1990s, the industry knew something about it that mattered here. Under sustained stress, in hot borated water, alloy 600 cracks. The mechanism has a name: primary water, stress, corrosion, cracking. And it is slow, and it is quiet, and it produces cracks you can only find by going up on that lid and looking. Which brings us to the second half of the geometry. You cannot easily go up on that lid and look. The head is covered by an insulation package and a service structure. To inspect a nozzle, you need access, you need time, and the plant needs to be shut down and cooled. Every hour a reactor spends shut down is an hour it is not selling electricity. Hold that thought. It comes back with a date on it. Now the record. In 1996, boric acid deposits are documented on top of the Davis-Besse head. That is the first entry in a paper trail that runs for 6 years. The deposits matter for 2 reasons. 1. Boric acid on the outside of the lid means borated water got to the outside of the lid, and the only way out is through a crack. 2. And this is the part that turns a problem into a trap. The deposits themselves block the view. Once the head is crusted, visual inspection for leakage stops working. The evidence of the leak becomes the thing that hides the leak. 1998. During that outage, the operator sees boric acid accumulation on the reactor pressure vessel head. It gets attributed to a leaking flange. The flange explanation is not crazy. It is also not verified. The head is not cleaned to bare metal. Nothing is opened up. The finding is closed. Then the plant starts complaining in a different language. Inside containment, there is a radiation monitor with filter elements. Those filters normally get changed about once a month. By May of 1999, they were being changed every 2 days, 15 times the normal rate. Something was loading those filters with particulate continuously for months. The containment air coolers tell the same story louder. Before 1998, according to the record reviewed by the Government Accountability Office, those coolers seldom needed cleaning. Between late 1998 and May of 2001, First Energy had to clean them 28 times. The fouling was boric acid. Read those two facts together and you have a machine describing its own injury. Boric acid was not sitting quietly on a lid. It was airborne inside containment in enough quantity to blind a radiation monitor every 48 hours and to plug the air conditioning of the building 28 times in 30 months, 2000. Refueling outage 12. Boric acid deposits are documented on the head flange region. An NRC resident inspector has shown rust and boric acid on that head. There is a photograph of it in the GAO report. The plant restarts in May of 2000 without the leakage being fully characterized and eliminated. 5 years later, when the NRC finally writes the penalty, that restart is the principal violation. $5 million of a $5.45 million fine hangs on that single decision. Going back to power in May 2000 with an uncharacterized leak on the reactor head. One more entry, and it is the one that explains the shape of the whole failure. The NRC regional branch chief who supervised the staff overseeing the head inspection work during that 2000 outage later said he was unaware of the boric acid problems at Davis-Besse, including the effects on the containment air coolers and on the radiation monitor filters. The information existed. It was written down. It was in maintenance records at the plant. It simply never crossed the 6 feet of hallway between a maintenance planner and a regulator. Now the physics, because you need to understand why a leak this small could remove that much steel and still leave the plant running normally. Start with the crack. A nozzle made of alloy 600 develops a crack from primary water stress corrosion cracking. At Davis-Besse, multiple head penetration nozzles were found cracked. Nozzle number 3 is the one that matters. The cavity opened up right next to it. Through that crack comes reactor coolant. Not a jet. Not a spray you would see on a gauge. A weep. The leak rate was small enough that it never tripped a limit, never forced a shutdown, never showed up as a number anybody had to act on. Here is what that weep does when it reaches the outside of the lid. The coolant is water with boric acid dissolved in it. On the far side of the crack, the pressure drops and the water flashes to steam. The water leaves. The boron does not. What is left behind on the steel is concentrated boric acid, held at operating temperature, continuously replenished by the leak. That is not a chemical spill. That is a chemical reactor you have accidentally built on top of your reactor. Concentrated boric acid at temperature attacks carbon steel aggressively. It converts steel to iron borate and iron oxide, the red-brown material that showed up on those filter elements. The corrosion product does not seal the wound. It flakes and washes and gets carried off, exposing fresh metal underneath. The reaction has a continuous supply of acid, a continuous supply of heat, and a continuous supply of new steel. So the wastage does not slow down. It cores. Think about a drip from a gutter joint hitting one spot on a concrete step for 6 winters. You do not get an even wear across the step. You get a hole where the drip lands. Same geometry here. The leak path fixes the location, and the location gets eaten while everything around it stays mirror clean. Down it goes, through 6.5 inches of carbon steel. The cavity that was eventually mapped ran roughly 4 by 5 inches at the base and opened wider toward the top surface. Something on the order of 20 to 30 square inches of missing structural steel, described in the Government Accountability Office's report as pineapple-sized. And then the corrosion stops. It stops because it hits the stainless steel cladding, the raincoat on the inside face. Stainless is far more resistant to boric acid attack. The chemistry that ate 6.5 inches of carbon steel could not get through a layer a fraction of that thickness, which sets up the exact situation in the photograph. The strong material is gone. The weak-looking material is holding. And what it is holding back is the full operating pressure of the primary system, about 2,000 pounds per square inch at over 500 degrees Fahrenheit. I want to be precise about that last layer because the reports are not identical, and I am not going to smooth that over for you. The Government Accountability Office describes the liner as a thin stainless steel lining, less than 1/3 of an inch thick. Other technical accounts of the same event give a thinner figure at the worst point, as low as 3/16 of an inch. The two numbers describe the same piece of metal measured different ways. Take the range. 1/3 of an inch is about the thickness of 2 stacked pennies and a dime, and it was not intact. Inspection found the cladding bulging outward, with evidence of cracking in it. That bulge is the most important detail in this entire case, and it is the one people skipped past. Cladding is not designed to be a pressure boundary. It is a corrosion barrier, a coating with a job description. Nobody engineered it to take 2,000 pounds per square inch across a 4 by 5 inch unsupported span. It was doing a job it was never rated for. It had already started to deform under the load, and it had begun to crack. If it had let go, you would not have gotten a leak. You would have gotten a hole in the top of the pressure vessel with control rod drive mechanisms and their nozzles above it. A loss of coolant accident at the worst possible geometry at the top of the vessel, with the mechanisms that insert the control rods sitting directly in the blast path. I am not going to tell you what would have happened after that, because the honest answer is that the analyses of exactly how much margin remained differ, and nobody has to speculate to see the point. The point is the number. 6.5 inches designed, 1/3 of an inch, bulging and cracked, delivered. So we come to the decision. This is the part of the case that has a date, a signature line, and a paper trail. And this is why we are doing this episode. August 3rd, 2001. The Nuclear Regulatory Commission issues Bulletin 2001-01 on circumferential cracking of reactor pressure vessel head penetration nozzles. It goes to pressurized water reactor licensees. Plants with susceptible histories are asked to report, within 30 days, their plans for inspecting those nozzles. And the bulletin sets a line in the calendar. Inspections before December 31st, 2001. Any licensee not planning to inspect by that date has to justify operating past it. Davis-Besse was among the plants the bulletin was aimed at, September 2001. The operator responds with a proposal: conduct the inspections in April of 2002, following a refueling shutdown already scheduled for March 31st, 2002. That is 4 months past the regulator's date. What follows is not a conspiracy. It is correspondence. Over the following months, FENOC, First Energy Nuclear Operating Company, sends the NRC 5 letters. The argument in them is consistent. Our past inspections were adequate. The head is in acceptable condition. We can safely run until the already scheduled outage. On the other side, NRC staff did not simply accept it. The Government Accountability Office found that the staff drafted an enforcement order, an order that would have required Davis-Besse to shut down by December 2001 for the inspection if the company could not adequately justify running longer. That order was written. It was not issued. Somebody wrote this down before it happened. Instead, the two sides compromised on a date, mid-February. The plant would shut down on February 16, 2002, and inspect the nozzles then. Now hold the two halves of this case next to each other, because this is the whole autopsy. On one side of the building, a lid that had been shedding boric acid since 1996, filters being changed every 2 days, air coolers cleaned 28 times, a resident inspector shown rust on a reactor head in 2000, and a restart approved that same year with the leak still uncharacterized. On the other side of the building, a technical argument, in 5 letters, that past inspections were adequate. The regulator later found its own analysis had not anticipated how severe the corrosion risk from a leaking nozzle could get. That is the failure in one line. The people arguing about the schedule were arguing about crack growth in a tube. The thing actually running was the destruction of the vessel head around the tube. They were watching the wrong clock, and they moved the deadline on the clock they were watching by 7 weeks. February 16, 2002. Davis-Besse shuts down and enters its 13th refueling outage. On the work list, inspect the vessel head penetration nozzles, per the bulletin, per the compromise. The head is crusted with deposits. Crews clean. Under the deposits, they find cracked nozzles. At this point, this is still a manageable outage. Cracked alloy 600 nozzles were a known industry problem in 2002. You repair the nozzle. That is what the crews set out to do. Early March 2002. Working on nozzle number 3, they go after the metal around the penetration, and the metal is not there. What is there is a cavity. It runs down through the full 6.5 inches of the carbon steel head. At the bottom of it, exposed, is the stainless steel cladding. The inner liner, a fraction of an inch thick that was never meant to see the outside world at all. And that cladding is bulging outward, with cracking in it. The reactor had run right up to that moment. Every gauge in the control room had been normal. Every operating limit had been met. Power had been on the grid. Somebody put a scale next to the hole and took a photograph. That photograph is the reason you have heard of this plant. Let me tell you what that image is, in forensic terms, because it is unusual. Almost everything I examine on this channel is a photograph taken after the failure. This is a photograph taken before it. Same as a crack found in an axle at the moment of teardown. It is the only kind of evidence that carries a number instead of a body count, and the number here is the thickness of a coating. The plant did not shut down because someone found the hole. The hole was found because the plant shut down. On a date that was itself the subject of 5 letters and a compromise, 7 weeks after the regulator's original line in the calendar, 4 weeks before the shutdown the company had originally proposed. Nobody in that outage picked the right date on purpose. The right date was picked in an argument about a different problem. Davis-Besse did not restart in 2002. It did not restart in 2003. It came back in March of 2004, roughly 2 years dark. The Government Accountability Office put the cost of the shutdown and restart preparations at about $640 million as of March 2004. The institutional record after the fact is unusually complete, and it is worth naming. On September 30, 2002, the NRC's Davis-Besse Reactor Vessel Head Degradation Lessons Learned Task Force reported its findings. It carried 51 recommendations for the agency itself, not for the utility. 51 on how a regulator assesses head integrity, weighs operating experience, and decides whether to make a plant stop. In May of 2004, the Government Accountability Office published GAO 04415 with 5 recommendations to the NRC covering resource allocation, management oversight, safety culture assessment, its procedures for shutdown decisions, and how it uses probabilistic risk assessment. The agency implemented them. In April of 2005, the NRC proposed a civil penalty of $5,450,000, the largest single fine the agency had ever proposed. $5 million of it for restarting and operating the plant in May of 2000 without fully characterizing and eliminating the head leakage. $450,000 for providing incomplete and inaccurate information to the NRC about the extent of the cleaning and inspection of that head in 2000. In January of 2006, First Energy Nuclear Operating Company agreed to pay $28 million in a settlement with the Department of Justice. And the industry changed the thing that actually caused this. Bare metal visual inspection of the head became the expectation instead of a look at an insulated package. Boric acid control programs stopped being a housekeeping matter. The materials themselves moved. Replacement heads went to alloys that do not crack the way alloy 600 cracks. Now the ledger. 0 dead. 0 injured. 0 radiological release to the public. That is the true and complete human ledger of Davis-Besse, and I want to be careful with how I hand it to you, because the temptation is to read that line as, nothing happened. Something happened. It happened to a piece of steel, over 6 years, 25 feet above a reactor core, in a building where hundreds of people worked, in a county on the shore of Lake Erie. The reason there is no casualty list is not that the system worked. The system had been told, in writing, 6 separate ways since 1996. The reason there is no casualty list is a stainless steel raincoat that held a load it was never designed to carry for however long it had left, until a compromise date on a calendar happened to arrive first. Count the margin. 6.5 inches designed. 1/3 of an inch delivered, bulging, cracked. The paperwork got the date wrong by 7 weeks in the safe direction. That is the entire margin of this story. I'm Ray Callahan. The documents are in the description.